Okay. Chapter 10 is about synthesis of the structure and synthesis of alcohol. Just like before, when I said whenever we talk about new family of organic molecules, we talk about the would be nice if the mouse works. Okay. For every family that we start, the new family that we start, we talk about the structure, hybridization, functional group. What's the functional group? And then physical property. Then we start about naming the group or members of the family. After we name the family, then we talk about how to prepare these compounds. And preparing the compounds, that means you have reactants that you start and the products are alcohol. Last part is like reactions of those members of the family. It means you take the alcohol as, in this case, you would take the alcohol as a reactant and see what you can do, what other compounds you can or functional groups you can convert the alcohol to. So the alcohol functional group would be converted to alkene or aldehyde, ketone, carboxylic acid, and others. Chapter of alcohol is divided two chapters. Chapter 10 is covered in Organic 1. Chapter 11 is covered in Organic 2 at Broward College. So the reactions of alcohol, you would start in the next chapter, next semester, or when you take your Organic 2, if you take it at Broward College. Everybody would start with the, just a refresher from Chapter 10, and then start with Chapter 11, reactions. So I'm just repeating the four aspects: the structure and physical property of the molecules or of the group, like alcohols. So we talk about the structure and physical properties. We talk about naming of these compounds, preparation of these compounds, how to synthesize them, and then reactions of the alcohols in the next semester. Functional group for alcohol is OH. So is the OH attached to the to carbon. So if you have a carbon-carbon bond that carries the OH functional group, the compound classifies as alcohol. The bond angle or hybridization for this for the carbon carrying, so it depends on the number of bonds you have for carbon. If carbon carries one pi bond or one double bond, is going to be sp2 hybrid. If all bonds attached to the carbon is a single bond, then is sp3. The hybridization for the oxygen is also sp3 and is expected to be 109.5. The observed or experimental value for the measured value for the bond angle for oxygen, the COH, is 108.9. It's slightly lower than 109, and the reason for that being slightly lower than 109 is the pressure that is coming from the repulsion forces between the two unshared pair of electrons you have on the oxygen. So it's trying to close this gap or close the angle, and it's going to lower it to 108.9. It doesn't lower much because at the same time you have the hybridization restricts, and then also you have a carbon group here. Is not just the hydrogen, because if it was just hydrogen, the bond angle would be much closer, much smaller compared to the 109, and that is like 104.5 comparing to 109.5, because this angle the force that is coming from, or repulsion forces between the pair of unshared electrons. So for alcohol, because we get one alkyl group, which is bulkier, at the same time, the steric hindrance between the alkyl group and the hydrogen, they're pushing each other out or away. It kind of opens up this bond angle compared to water. So if you're comparing the angle for water to alcohol, you see for alcohol is slightly higher. Talk about the alcohols. We do have primary, secondary, or tertiary, and how do we determine the degree or classification? Is it primary, secondary? If the carbon that carries the OH is a primary carbon. What is a primary carbon? Primary carbon has one carbon-carbon bond, only is attached to one other carbon. A secondary carbon would be a carbon that is attached to two other carbons. So we have two carbon-carbon bond for this secondary alcohol. The carbon is secondary, and since the carbon is secondary, the alcohol is also secondary. So if OH is attached to a secondary carbon, is secondary alcohol. If the OH is attached to tertiary carbon, so this carbon is tertiary, the alcohol is tertiary. So OH is attached to tertiary alcohol. So phenol is when you have the benzene ring and you have the benzene ring that carries the OH. So if OH is attached to benzene ring, the classification is specifically is an aromatic alcohol, and it's known as phenol. Just to get some basic information about the alcohol. Alcohols, they do have OH group, and with the OH group, it makes the type of intermolecular forces H bonding. So we have H bonding as the intermolecular force or major intermolecular forces. So comparing to alkane, ether, or compound, other compounds that they have similar molar mass, but they do not have hydrogen bonding. Alcohols, they have higher melting point, higher boiling point, because the hydrogen bonding is a stronger intermolecular force compared to van der Waals forces and dipole-dipole interaction. So the hydrogen bonding, which is the major and intermolecular force, the minor intermolecular force would be van der Waals forces, or the London dispersions, actually, that is increasing based on the molar mass. So it depends on the size of the carbon chain that can change, but hydrogen bonding is strong, and it is the major intermolecular force for alcohols. And that gives a specific property to alcohols: one, higher boiling point compared to the other compounds that they have similar molar mass, but they don't have hydrogen bonding, like alkane, alkene, or ethers. And second, solubility. Alcohols are more soluble in water compared to alkane and ethers because, or hydrocarbons and ethers, because of the hydrogen bonding. The rule for solubility is like dissolves in like. So water has hydrogen bonding, alcohol has hydrogen bonding. As a result, when we have a OH group for the alcohol, it makes the molecule more soluble in water compared to comparable molar masses with the other functional group that does not carry H bonding. Solubility, it does increase based on the hydrogen bonding, but the cutoff is like 5 carbon. So if you have a 1 carbon alcohol, highly soluble in water, highly soluble. Now, if you change that to C2H5OH, which is ethanol, is going to be soluble propanol soluble, and then you go to butanol. Butanol is going to be less soluble than propanol, or in general, as you increase the carbon chain, the solubility is going to decrease. Why solubility is decreasing? Because when you are looking at the molecule of alcohol, you do have a polar head. So you have a polar side, and then non-polar tail, non-polar. So you have non-polar and the polar side. Your molecule has two sides. Now, if the non-polar side, it gets long. So if you have like 6 carbon alcohol, 7 carbon alcohol, then the non-polar part is going to be more significant than the polar side of the molecule, and your molecule is going to be insoluble in water. So as you increase the number of carbon in the carbon chain, the solubility is going to decrease. Okay, that's for some physical properties. Boiling point is high compared to the others because of the hydrogen bonding. Now, how would you name these compounds? For the IUPAC naming, you always look for the highest and for the longest carbon chain. Second rule, you're going to number your carbon chain in a way that the functional group is going to be attached to takes the lower number, lowest possible number. It cannot be always 1, but lower possible number. If you have a long carbon chain and you have a carbon chain that is shorter, but it takes the OH, then that takes the priority. So you must include the high priority functional group as the main carbon chain. So the example that we have on here, I'm just going to work out the same example first, and I bring new examples. So you have carbon 1, 2, 3. OH is on carbon 1. And any carbon that does not take a number, it becomes a branch. So OH is on carbon 1. It could have been on carbon 2 also. So we have to specify OH is on which carbon. The methyl group is on carbon 2. That's the only other branch that we have. So we are going to start with location of the branch first, name of the branch. Then for the functional group, you have to indicate that this functional group, it's on carbon number 1. So it's 1-propanol. How do you come up with the propanol? So you have the propane, you drop the E and add OL. You have to also give the location to the OH. Is it attached to carbon 1 or is it attached to carbon 2? It doesn't make to say it's attached to carbon 3, because if it's attached to carbon 3, then you will start numbering from the left side, it becomes carbon 1. So you give the location to the functional group, then you would say propane, you drop the E and add OL. For butanol, how would you, for the second compound, to name this compound, you have 2 choices, like 1, 2, 3, and 4, and the other choice would be 1, 2, 3, and 4. So we have to number it from left to right, because if we number from left to right, OH is going to be on carbon number 2. So this is going to be wrong. You cannot go from the right to left. You have to number from the left to right. There is no other branches. When you number it, all carbons would take the number. So there is no other branches. You give the location of the functional group of the alcohol, and you separate the number by dash line and butanol, because if you have the butane, you drop the E and add OL. Now, butane 2-ol. This one is like a newer IUPAC rule, and we still have the old one and new one, both of them. In most of the books, they cover both of them. because 1997, which is relatively very new compared to the other rules that we have about 100 years old, or more, they said that we could also use a new naming system. This is good when you have more than one functional group. So you could say like OH is attached to carbon 2, and then like the alkene group is attached to carbon number 4, and so. But if it's just one functional group, for me at least, it's easier to go with the 2-butanol rather than butane 2-ol. It kind of rhymes better for me. Both of them are acceptable. Just to, okay. For this tertiary alcohol, you have to start numbering the carbons like 1, and it doesn't matter which way you number it, you end up with 1, 2, and 3, and one methyl group has no number, so that becomes your branch for the molecule, and then the name of the branch is methyl group, location is 2-methyl, and the OH is attached to carbon 2 is 2-propanol. So if you look at the classification, this is a primary, and the second one is a secondary, and this one is a tertiary alcohol, just as a practice. If you have, now that you learn about more of functional groups, then you have to also find out which one is major functional group, because if OH is major functional group, you have to number from right to left. If alkene is the major functional group, then you have to number it from the right to left, from left to right, closer to the alkene. So OH in this case takes higher priority. OH has to be on lower number compared to the alkene functional group. So you must number from right to left. So you give location to all functional groups. If there is any branch, which in this case, when you have the number, when you number the carbons, there is no branches. So you have your OH on carbon number 2 and alkene on carbon number 4. So for the alkene, you just give the location of the starting carbon. So if the carbon double bond is between carbon 4 and 5, you don't have to say 4,5 alkene. That means that you have diene. So you just say 4 in. That means that this double bond started carbon 4 and it ends with carbon 5. It is understood that it's going to be between 4 and 5. If you say 4 butene or 4-hexene, that means that it's going to be between carbon 4 and 5 of 6-member ring or open chain. So you have to give the location for the functional group, which is 2-ol and 4-in. So 5-carbon chain, pent, 4-in, 2-ol. Okay. Or you could say 4-pentene, 2-ol. So you have 2 functional groups. You have to give location both to both functional groups. Since you have now you learn about the different functional groups, you have to be able to determine what takes the priority. So alcohol, it has on the priority list is much higher than alkenes. It's like 2 higher than alkenes. And then between alkenes and alkyne, you have to be worried about these 2. The ones that you learn in this organic one is alkyl halide, ethers, alkane, alkyne, alkene, and alcohols. The other 4 you are going to learn in organic 2. So for the ones that you have learned in this course, you must know the priority. So far, alcohol has the highest priority. So what does it mean? It means that if your molecule contains 2 functional groups, you have to focus on the one that has high priority in terms of starting for the numbering system. And if you have higher order functional group or high priority functional group with the alcohol, just like the example that it shows here, then you would name your compound with the higher order or higher priority functional group, which is carboxylic acid. Carboxylic acid is always number 1. So you would name it, and then OH becomes a branch. So you would name the OH as a branch. And since it's on carbon number 4, is going to be 4-hydroxy. So you just give the number and say that is the hydroxy. So we have 1, 2, 3, 4 carbon, and is butanoic acid. So that is like a butane. And you don't have to know about the naming of carboxylic acid. Just know that carboxylic acid has high priority compared to your OH. You drop the E and you add oic acid. Okay? So if you have 4 carbon acid, it would be butanoic acid. And then if you have 3, it would be propanoic acid. Basically, you would say propane. Then you drop the E at oic acid. Oic acid. Propanoic acid, or butanoic acid, pentanoic acid. So if the OH becomes a branch, that means your molecule contains one of these high priority functional group, and then you would use that. Use that as a branch, or name it as a branch. Okay, what would be the name for this compound? Which side should I number it? If I number from left to right, 1, 2, 3, 4, 5, I have 5 carbon. From right to left, 1, 2, 3, 4, 5. Which one is correct? From left to right, A, or right to left, B? Which one would be correct? So in either case, OH is going to be on carbon number. Okay, so either case, the OH is going to be our carbon number 3. I was looking chat box to see if you have an answer there. OH would be on carbon number 3. If you go for this route, going from right to left, you would have the methyl group on carbon number 2. But if you go from left to right, methyl group would be on carbon number 4. So the point of difference is the location of the methyl group. And since the going from right to left would give lower number overall, we have to look the use the numbering from the right to left. And if you do that, you are going to have 2 methyl or methyl group on carbon number 2. And then you have a OH group, which is alcohol, on carbon number 3. So you would say 3, and you have 5 carbon, pentane. You have the E, drop the E, and add OL, pentanol. So 2-methyl 3-pentanol. You don't have to show that you are dropping the E and adding OL. You can do that at just, mentally. Drop the E and add OL. Questions? No, the OH doesn't have to be the first. You don't have to write it because that's the main that was the main carbon. That's part of the main carbon chain. So your main carbon chain is going to be the 5 carbon, including OH. That's the main carbon carbon chain. So you have the 3-pentanol. Okay? You have your 3-pentanol, and 2-methyl is attached to 3-pentanol. 2 methyl, or methyl is attached to carbon number 2 of 3-pentanol. Yes. Any other questions? So if you have an OH group on a 6-member ring and you have, let's say, methyl group here, you would start from the carbon 1 OH, because it's the high priority functional group, would take carbon 1. So you have 1, 2, and 3, 4, 5, 6. Going down would be the proper way, or like clockwise would be proper way, because you want, if the OH is on carbon 1, methyl group to be on lower number, and that is a 3. So in a cyclohexanol, you don't have to say that OH is on carbon 1, because it's understood OH is going to be on carbon 1. 3-methyl cyclohexanol. So you don't have to say that OH is on carbon 1. It is understood. In a cyclic system, a CC double bond is always on carbon number 1, starts with carbon 1, and then alcohol starts in carbon 1. So it is understood. There's no need to say 1-hexanol. Any questions? If you have a diol, what it means is that you have 2 OH groups. If you have 2 OH groups, then you have to give the location to the OHs. And you want to go with the lowest possible number set again. If it's, both of them are 1 on each end, like this example that we have, you don't have much of a choice. So it's on carbon 1 and carbon 6. Just pay attention that if you have like functional group and like a chlorine or OH on this beginning or end of the carbon chain, when you are counting, immediately after this is a carbon. There is no carbon right here. The last one, if it's shown with the bond, is just a functional group or is a branch that it needs to be shown, and then it ends. You have a carbon here, so OH is attached to a carbon. So starts with a carbon, ends with a carbon. So you have hexane, because it's 6 carbon, and then location of the diols, 1,6-diol. The common name for alcohols, it's like methyl alcohol. Okay, so you would just say alkyl alcohol, methyl alcohol, and that would be for CH3OH. You could have ethyl alcohol, isopropyl alcohol, isobutyl alcohol. So it depends on the carbon chain that the OH is attached. So in this case, if you have like an isobutyl group carrying the OH, is called isobutyl alcohol, because if this branch was attached from this carbon to another main carbon chain, you would name this as isobutyl. The alkyl group was isobutyl. But if it's attached from the second carbon, that would be like sec-butyl. And since OH is attached to the second carbon, it's called sec-butyl alcohol. So if you see this alcohol extension or the suffix, that means that you are dealing with common name, is not the IUPAC name. Where the IUPAC name, you end up, your molecule ends up with OL or like a diol if you have more than 1 OH group here. So you have 6 carbon in this cyclic system. You have 1, 2, 3, and 4 carbon. You have 1, 2, 3, 4 carbon here. And if you number from the, and 6 carbon. First of all, which one is the major part of the molecule? The part that contains the OH or the part that contains more carbon? Because OH has high priority, Thank you. Because OH has high priority, then we have to look for the, we have to take this site as the main carbon chain. So this site A would take the priority. So we have the, even though we have more number of carbon, but still would count as a branch, and we name this as a cyclohexyl. Now, when you are numbering, should you number from right to left or left to right? If you number from right to left, you get the OHs on carbon 2 and carbon 4. If you number from left to right on this carbon chain, you get 1, 2, 3, and 4. So the OHs would be on carbon number 1 and 2. So numbering from left to right is more proper. So you want to make sure that the OHs, they fall on the low carbon with the lowest number. So you have now your cyclohexyl is attached to carbon 1. That's why you get 1 cyclohexyl, and then you have 4 carbon, which is butane, and 1,3-diol. OH is on carbon number 1 and 3. For cyclopentane, you have two OH groups, so it's going to be cyclopentane 1,2-diol because they are in 1 and 2 position. One is coming toward you, one is going away from you. So that makes it trans. If you were given the same structure, okay, same structure, but like a straight line was used for both of them, you didn't have enough information to name it cis or trans, then in that case, 1,2-diol or cyclopentane 1,2-diol would be sufficient. You didn't have to say cis or trans, but when they give the 3D structure, it's kind of a hint that you should give the cis or trans. The vicinal diols. What does it mean, vicinal diols? Meaning that OH are adjacent carbon. So it's like a 1, 2 here is known as the glycol. So if it's just the 2 carbon, it's called ethylene glycol. And ethylene glycol is the same thing as the main ingredient for the antifreeze. Why they are adding the antifreeze to radiator for a car for hot summer in Florida or very cold winter in North, because if you have 2 OH group, that means the hydrogen bonding is much stronger. And if the hydrogen bonding is much stronger, that means it's going to boil at much higher number compared to 100 that you have for water, or you have 78 for ethanol. So ethanol boils at 78 degrees Celsius. That's the boiling point. Water boils at 100 degrees Celsius. That's for boiling point. Ethylene glycol, I believe it has like a 200 degree Celsius of the boiling point. And since the boiling point is very high, they are using as the antifreeze. That means that it doesn't freeze. At the same time, it's understood that it has also very high boiling point, because for hot weather, we need something that doesn't boil at Florida hot day in the car, so it doesn't make the car very hot. So glycols are vicinal diols. So ethane 1,2-diol, and if you say ethylene glycol, that's the common name as well. If the OH is attached to the aromatic ring, is named as a phenol. So when you say phenol, it covers the benzene ring and it covers the OH. So you just say phenol, okay? And then it is understood that this is on carbon number 1. You don't have to even say 1 phenol, because OH is on carbon 1, of course. And then you just have to number it from the side that for clockwise or counterclockwise to get to the other one, the fastest or shortest. So it would be 1, 2, 3, 4, 1, 2, 3, 4, both sides same choices. So you have 4 methyl phenol. And then you have, in this case, you have 3 chloro phenol. So you don't have to bring the number. And also when you say phenol, it is understood that is a benzene ring attached to OH. This designation, just remember in case if you see it, aromatic is covered in organic too, but this prefix of para can be used whenever you have like a 1,4 substitutions. If you have di-substituted benzene ring and the position is like a 1 and 4, it's known. If you just say para, that means that these two are in 1,4 position. If you say meta, that means they are in the 1,3 position. If one is on carbon 1, the other one is on carbon 3. So you have 1,3 or meta, 1,4 or para, and then 1,2 would be ortho. Okay, 1,2 is ortho. Okay. For naming this compound, if we start from here, 1, 2, 3, 4, 5, and 6. If you start from the carbon up here, 1, 2, 3, 4, 5. Which one takes the priority? 6 carbon, which is a longer carbon chain, or the OH group. So you have to pay attention that the OH group would take the priority. And what about the halide that we have here? Should we start from this carbon and go up here and say 1, 2, 3, and 4, or go straight? Alkyl group, they don't have much higher priority compared to when you have a longer carbon chain, a choice. You have two choices. One choice would give you longer carbon chain. The other one would include the halide. You have to go with the longer carbon chain. But when it comes to CC double bond, it takes priority over long carbon chain. OH takes priority over long carbon chain, but halides are not that significant, so it doesn't take priority over long carbon chain. Any questions? Okay. We did talk about the boiling point and physical property for other, comparing alcohol to alkane and ether. Alcohol has much higher boiling point, and that is due to the hydrogen bonding. Solubility. If it says miscible, that means that it's highly soluble. It mixes like truly. You have like even and clear solution. So for the first 4, it would be. And then if you go from 4 to more, you are going to see that is going to be the solubility is decreasing. So the reason you have here for 1,6-diol is miscible again. This is like propanol, because for 6 carbon you have 2 OH group. That's kind of explaining that for each 3 carbon you have 1 OH group. So the solubility is similar to the propyl alcohol. Okay. So solubility is going to decrease as the main carbon chain or the hydrophobic region of the molecule, it gets longer or takes the priority. Commercially important alcohols. Methanol is known as wood alcohol. Ethanol is the only edible alcohol. And the production of this it can be is synthesized in industry from gas, and then the usage, they are good solvent. And beside being consumed as like an edible alcohol, it has some industrial application as well. So the 10% ethanol in the gasoline is increasing the combustibility, so it makes it more, better mile per gallon. It gives you better mile per gallon. So the toxic dose, meaning that 200 milliliter, if someone, average person, which average weight consumes 200 milliliter of pure alcohol, it can go to coma. It's very toxic at a very high level. So again, there's like a term called LD50. That's like when they say like toxic dosage, that means that the effect on 50% of the population was lethal. So it's dangerous to have very high volume of it consumed at once. Methanol is a toxic alcohol. So is the wood alcohol. It does cause blindness and death, at the higher dose. So toxic dose is much lower here for the 100 milliliter, but at even lower than that, it can cause brain damage and cause blindness. So it's different. The properties is different. The reason for that is that methanol in the body, it would change to methanoic acid. Methanoic acid or formic acid. That's another name for it. Methanoic acid or formic acid. But this one, ethanol, would give you ethanoic acid. Ethanoic acid, same thing as acetic acid. Methanoic acid is the same thing as the formic acid. Where do you find formic acid other than the labs? You would find it in the, when you get the bite mark from fire ants, they inject formic acid. If like high number of fire ants, they attack a person at the same time, and they inject enough formic acid, actually cause death. Is very, very toxic. But acetic acid is the other place that you could find the acetic acid is in the kitchen. Actually, 5% of it is vinegar, and it's edible also, is edible acid. So in the body, like when you consume it, ethanol would give you ethanoic and methanol would give you methanoic. And the methanoic acid is very, very toxic. That's why the toxic dose for methanol is much lower compared to ethanol. The acidity for alcohol, it's very, very low. So you have the pKa of 15.5 for methanol, and then the pKa is is almost about the water. The only one that you get better pKa or more acidic than water is because for water is 15.7. So if it stays around 15.7, that's like close to neutral. That's for acidity. But if it's 10, that's like much higher acidity compared to water, or much higher acidity compared to the cyclohexanol. That's like 100 million times more acidic for phenol. The reason phenol is more acidic is when when phenol loses hydrogen, changes to phenoxide, and phenoxide, it can actually form resonance, multiple resonances. And because it's forming multiple resonances, as a result, it can give you more stable intermediate that is forming the phenoxide. And since it's more stable, so the compound is acting as a stronger acid. But the acidity of other alcohol, they are not very acidic. They are lower acidic. If you have electron withdrawing group attached to any molecule that carries OH, it's going to increase the acidity. So if you have a compound with OH, 3-carbon OH, and you have another one with 3-carbon OH, but there is a, like, let's say you have fluorine attached to this, it's going to be more acidic, okay? More acidic because you have the fluorine attached here. Electron withdrawing group is going to increase the acidity. So first of all, you have to have the ionizable hydrogen, means you have to have the OH, and then you have to, if you're adding electron withdrawing group, is going to be a lot more acidic. So if you're comparing 1 chlorine with 3 chlorine attached, this is changing by 100 times more acidic. So when you're taking the pKa value, that's like a negative log, and 1 difference, that's like 10 times, 2 unit difference, that's like 100 times. 8 times difference, 8 difference in the pKa value, that means 100 million times. So that's 10 to 8 value difference in time, in multiple, basically. Carboxylic acid is more acidic. HCl, of course, is just saying that how acidic is water compared to the other alcohol and the acids. And how would that acidity of cyclohexanol versus phenol is going to work in a chemical reaction? In a chemical reaction, if you have phenol, you don't have to bring like sodium or potassium to change to phenoxide. You can just use sodium hydroxide. With sodium hydroxide, phenol can change to phenoxide. But if you have cyclohexanol, because it's very weak acid, so you must use very strong base. And that very strong base is using sodium or potassium itself. You cannot use sodium hydroxide solution or potassium hydroxide solution for cyclohexanol to remove the hydrogen. That just shows how weak of an acid is cyclohexanol compared to phenol. And the reason I already talked about is the formation of resonance for phenol after losing the hydrogen, where for the other one, you don't have it. So if you add very strong base to alcohol, you can remove the hydrogen. And when you remove the hydrogen, now you change that to alkoxide in general. So etoxide for 2 carbon, methoxide with 1 carbon, but alkoxide in general. Alkoxide, they are very strong nucleophile. We have used them before for the SN1, SN2 reactions as the nucleophile. But how do you prepare them? Now you learn about how to prepare alkoxide. Like if you want etoxide, how would you prepare it? You start with ethanol, you add sodium or potassium, it would remove the hydrogen and it would change to etoxide. And weak acid, strong base, conjugate base. At the same time, this is also a strong nucleophile. It's a strong base and a strong nucleophile. We look at chat if there is any questions here for me. Yes, exactly. Very good. I see the comments. Not much of a question, so thank you for response. Okay, this slide, it shows all the resonances that a phenoxide can form, and that's like 4 of them. The greater number of resonances, the more stable the intermediate is going to be. And if you have this double arrow, it shows that they are related. They are resonance. And if they are resonance, how do you go from one resonance to the second resonance? When you have negative charge on the oxygen, pair of electron can drop in. When pair of electron drop in, the pi bond is going to move up, because when the pair of electron drops in, it's going to form this double bond here. You get that double bond. What's going to happen to this carbon already has 4 bonds. If you count it, you have 1 double bond and 2 single bond, that's 4 bonds. When you get the 5th bond, it's going to make this carbon very unstable. So the weakest bond has to break. What is the weakest bond? Is a bond to oxygen, bond to carbon, or bond to the other carbon? So to the other carbon, we have 2 bonds. One is sigma, one is pi. The pi bond is the weakest bond. And as a result, the pi bond is going to, pi bond basically is 2 electrons. So the pi bond is going to move to the carbon. So the pi bond is moving by 1 space. That's the net result. The charge is jumping by 2. So the charge from oxygen jumping to carbon, but the pi bond is kind of moving by 1 unit. So pi bond is moving. Now, if you bring going from resonance 2 to resonance 3, dropping the pair of electron from carbon again, you get the double bond. The pi bond is going to move to the next carbon, and you get the new resonance. When it gets to the case that if you bring it back, is going to form the same molecule, then you stop, because this can rotate like multiple times, but you can't take the credit. The molecule cannot take the credit to have like 100 resonances. It will stop when the next move is going to take it back to the original one. So you only have like 4 resonances in this case. And because it's a stronger acid, it can actually, the hydrogen can be removed by sodium hydroxide, and you get the phenoxide as the product. To synthesize alcohols, you have seen some of these reactions already. One is to hydrate alkene. When you hydrate alkene, you have 3 ways to hydrate alkene. One is use H2OH+. This is called direct hydration. You're adding water in acidic solution. Second, you would use oxymercuration, demercuration, which you have to memorize the reagents. Third, you would do hydroboration oxidation. So you would use the oxy, D, and then hydroboration oxidation, and direct hydration. Chance for rearrangement. Rearrangement is a possibility. No chance for rearrangement. Oxymercuration, demercuration, and these 2 are mark addition. And this one is anti-mark. This one is anti-addition. That means one is added from top, the other one from the bottom. This one is mix, and this one is a syn addition. Okay, so we have syn addition, anti-addition, mix. The 2 of them are Markovnikov. One is anti-Markovnikov. Chance for rearrangement. So there is a possibility for rearrangement if you go from primary carbocation to secondary or tertiary, or the carbocation would increase. So we learned about the hydration already. We also, from chapter 8, you learned that if you have a CC double bond and you do osmium tetroxide, you can change to diol. If you have a CC double bond and you change that to, you use cold permanganate, you would also change that to diol. So from this, you can get the diol as well. And the same thing, For osmium tetroxide, if you are using OSO4, you would get syn addition. Okay. So this is a syn addition also. And if you do the other way, is to change to the first, you change to epoxide, and then you hydrolyze it. Now, in this case, you would get the anti-addition of the OH. So for the adding OH or adding two OHs, these reactions are reviewed from previous chapter, from chapter 8. So any of these reaction can be a part of the chapter 10, like a quiz or questions, but is reviewed already. Okay, it's a review from before. Any questions for me? Okay. If you don't have questions, I can go over one of the organometallic reagents and like have to prepare alcohol using organometallic reagents. When you say organometallic, that means that there's a metal attached to the carbon. And what makes it, like, how unique is that, is the fact that when you add the metal to carbon, metal would take positive charge, and carbon, as a result, would take negative charge. So okay. So you have carbon positive charge and then the metal carbon negative charge, sorry. So if you have molecules that they could have carbon with a positive charge. So example, halide, they have highly electronegative. So as a result, carbon would be positive charge. Oxygen is highly electronegative. So carbon is going to be positive charge. So these are partially positive carbons. So if you were looking for partially positive carbons, you have to look for carbon that is attached highly electronegative element. Now, if you are looking for carbon with negative charge, you have to have a metal attached to it. So if metal is positive, the carbon is going to be negative. If carbon is negative, then that carbon acts as a strong nucleophile because it's negative charge. It's not even partially. When you have a metal, non-metal, you have ionic bond here. And if it's ionic bond, then you have charge separation. So metal takes the positive charge, carbon will take the negative charge. So the other case that you could have carbon with the negative charge is using of acetylide. And the acetylide is, if you have acetylene, hybridization for carbon is sp. High S character of the carbon carrying the hydrogen is going to increase the acidity. So we have, this is going to be a lot more acidic than the CC double bond, or when you have sp2 hybrid. So this hydrogen is acidic hydrogen. If you add a strong base, you can actually remove the hydrogen. And when you remove that hydrogen, you are going to end up with negative charge on carbon. So to remove that, you have to bring in a strong acid like a sodium amide. Ammonia is very strong. It's not a very strong, but it is a strong, is a base. Obviously is a base, okay? Is an obvious base. Sodium is a base. If you add base to acid, it neutralizes, but if you add base to base, it's going to make it a stronger base. So sodium amide is one of the other strongest strong base, just like sodium or potassium itself. So it can remove hydrogen from weak acids. When it does remove, it's going to change to strong base. So weak acid, strong conjugate base. Now, if you have a strong conjugate base with the carbon is negatively charged, this negatively charged carbon is acting as a strong nucleophile. A strong nucleophile, if we bring a nucleophile, it can attack the positively charged or partially positive carbon. You can find that in alkyl halide. You can find that in carbonyl compound. So it can attack either one of them. Okay? What happens if nucleophile attacks alkyl halide? When the nucleophile attacks the alkyl halide, then leaving group is going to leave. When nucleophile attacks the carbonyl group, the pi bond will break over the oxygen. So that's the major difference. Okay? If you don't have leaving group, the pi bond will break. If you have a leaving group, the leaving group would leave. But the basic structure or the mechanism for this reaction, first of all, you have to create your nucleophile. How do you create your nucleophile? From a terminal alkyne, you add a strong base, you get the acetanilide ion, which is a strong nucleophile. This is a strong nucleophile. Your strong nucleophile, it can attack the alkyl halide. If it does attack alkyl halide, the halide would leave as the leaving group, and you have a new carbon-carbon bond. So you see that in this case, the blue color is coming from acetanilide. Basically, you're adding is a terminal alkyne. Depends, you have one carbon, two carbon, or if this is even hydrogen. But the alkyl halide also brings other carbons. But the net result that you're adding to the carbon chain because you are creating carbon-carbon bond. And the other unique property is that here you're adding a new functional group of alkyne. So if you had an alkyne with 4 carbon and you wanted to make an alkyne with 8 carbon, then you would use this method to increase the carbon chain of alkyne. Or in general, you have these, nucleophilic attack to carbon that is partially positive. For carbons that are partially positive, I'm repeating again, these are 2 examples, 2 good examples, they are very common. Carbon must have positive charge, partially positive charge. If nucleophile or strong nucleophile, if it attaches or attacks the alkyl halide, halide would leave as the leaving group. But if it does attack carbonyl group, there is no leaving group here. Leaving group must be stable on its own. So the pi bond will break over the oxygen. You get the alkoxide. On the next step, you can just add a hydrogen to it. You can bring the solvent. So when you are doing this acetanilide plus the ketone or aldehyde or formaldehyde, next step would be hydrolysis. Then you hydrolyze it and you would go to formation of alcohol. So if the strong nucleophile or organometallic compound attacks the carbonyl group, your product is going to be alcohol. Questions? Chat box. Any questions? Okay. Yes. Lab 9, you have in lab 9, you have nucleophilic substitution reactions, either SN1 or SN2. When the nucleophile comes in, the leaving group would leave, and then you get a precipitate, yes. And then you count for how long does it take for that precipitate to form, yes, just like lab. So acetanilide, so if you have the RCCC minus, that's a nucleophile that is you can bring from the terminal alkyne. The other strong nucleophile is is called Grignard reagent, and Grignard reagent is alkyl halide. You have alkyl halide, you add magnesium. So what happens? Magnesium doesn't, react with this to give like two products. Magnesium basically is going to be inserted between the alkyl group and the halide. So you get like R general formula, RMGX. So you start with the RX and you end up with RMGX when you add the magnesium. So Mg is going to be plus charge. That's a negative, that's halide. Also, the R is going to be negative. So if you insert the magnesium between the carbon and hydrogen and the halide, it could be iodine, bromine, or chlorine. You are going to create negative charge on this carbon, and that part of the molecule is going to act as a strong nucleophile. So we create the nucleophile. As soon as you create the nucleophile, now you can attack that nucleophile, can attack that carbonyl group, or it can attack a alkyl halide. So nucleophile is going to be created as you insert the magnesium between the carbon and the halide. The good thing about this Grignard reagent, it can go from like open chain alkyl halide, from cyclic, it can go from aryl halide, and it can be like a secondary alkyl halide. It can go from like a vinylic. So there is no really limitation for that. So these examples is just saying that how good you can plan your experiment or your reaction by generating Grignard. All of these are possible. There are some limitation, but but at the same time, it has a lot of options that you can create Grignard reagent. And it doesn't matter how you create the Grignard reagent, the carbon directly attached to the magnesium is going to be negatively charged. So you have negative charge there, negative charge, and negative charge here. So this piece is nucleophile. Okay, this piece is nucleophile. Okay. Because you have a negative charge on this carbon. The new carbon-carbon bond is going to initiate or is going to form from the carbon that is directly attached to the magnesium to the carbon that is partially positive from the CO. That's the new carbon-carbon bond that is forming. Okay, I'm going to stop here because I don't want to take the